today's notes are going to cover our final two transformations, symmetry and dilations. So first, let's start with symmetry. There are three types of symmetry: line, point, and rotational. Line symmetry is when a figure can be reflected onto itself through a line. So that could be a horizontal, vertical, diagonal, whatever it may be. So in this case, if I look at this triangle, if I were to put a line down this figure and fold that triangle over, that triangle would lay perfectly onto itself. So this triangle would have line symmetry. When I look for point symmetry, a figure has point symmetry if the figure is mapped onto itself by rotating the figure exactly 180 degrees. So that means it's going to look the same upside down. What I do is I take like a mental image of the figure, and then I flip my figure over 180 degrees, and I see if it looks the same. What I'm going to do right now is I'm just going to look at my end, and then I have an end over here. So I'm going to flip my end over, and if you notice, yes, it looks the exact same. So this would have point symmetry. Then the last type is rotational symmetry. This exists if a figure can be mapped onto itself by rotating it any amount less than 360 degrees. So at any point as I'm rotating my paper, if it looks the exact same as what it looked like originally, then I can say it has rotational symmetry. So if I'm looking at my sun, if I rotate it, boom, right there, it looks the exact same. So it has rotational symmetry. And in fact, this one has a lot of rotational symmetry. Because right here it looks the exact same, right here it looks the exact same, right here it looks the exact same. So this has a lot of rotational symmetry. And in fact, something to note is that if it has point symmetry, so if you can rotate it 180 degrees and it looks the same, it's automatically going to have rotational symmetry. Because I rotate this 180 degrees, and boom, my sun looks the exact same. So that is something that we could note here. That's a really important fact about our symmetries. So if it has point symmetry, it also has rotational symmetry. And that's always the case. Now this doesn't go the other way around. So I can't say because it has rotational, it also has point. Because rotational isn't an exact value of 180 degrees like point is. But that 180 degrees falls into the value of less than 360 degrees. So just make sure you keep that in mind. It works every time it has point, it has rotational, but not every time it has rotational as a point. So let's look at a few examples. On number one, can this have a line that gives it line symmetry? So if I look, I could draw a line horizontally and it would fold. I could draw it vertically and it would fold. We only need to identify one line, so yes, this does work for line symmetry. If I go to rotate it, if I rotate it all the way around 180 degrees, does my figure look the exact same? Yes, so it has point. And since it has point, it also has rotational symmetry. So in this case, this one will have every single one. On number two, I could draw a line down the middle. So yes, it has line symmetry. I check for point symmetry. If I flip this guy over, no, it does not look the exact same. So it does not have a point. But at any point as I'm rotating it, does it look the exact same? Yeah, right there. So this one would have rotational. So this is an example of having rotational but not having point symmetry. Number three is a parallelogram. You actually can draw no lines of symmetry in a parallelogram because of those angles that aren't going to be congruent and our opposite sides that aren't going to be congruent to each other when you fold it either. So you're going to try to fight me on that one, but it does not have line symmetry at all. If I look for point symmetry, I flip it over. Yes, it looks exactly the same. So it has point, which therefore means it has rotation. On number four, if I try to draw a line in there, I'm not going to be able to do it. If I look for point symmetry, no. And if I reset and at any point it looks the same before I get back to my starting point. Nope, didn't look the same until I got back. So this one would be an example of that. On 5, your star. We can draw lots of line symmetries in a star. We can do vertical. So that's just one example. So we would say yes to line. If I take point, rotate it, doesn't look the same. I have 2 points instead of 1 point. So not point symmetry. At any point as I'm rotating, does it look the same? Right there. So this is another example of having rotational but not having point symmetry. On number 6, we do not draw a line anywhere. If I want to draw a line vertically, my curly cube would now be lined up horizontally, diagonally, because of this part right here is too specific. That would not line up either. So we do not have line symmetry. If we look for point symmetry, flip it 180 degrees, does it look the exact same? Yes, it does. So since it has point symmetry, it also has rotation symmetry. The letter A, I could draw a vertical line, and that would fold onto itself. So line. And I can rotate it 180, doesn't look like itself. And if I rotate it at any point, nope, not until I get back to the beginning. So this one only has line symmetry. And then number 8, I can't put a line and line anywhere. If I did point symmetry, 180. Nope. At any point as I'm rotating it, doesn't look the exact same before I get back to the center. Nope. So this one would be another example of line. Alright, I want you guys to turn the page and go ahead and pause the video and try to do these next 6. So 9 through 14, and I'll put the answers for you to check, but try to do the last 6, 9 through 14. Alright, so if you check your answers, 9 has point rotation, 10 has all 3, 11 has none, 12 has line, 13 has line and rotational, and 14 has point and rotation. Alright, so if you're noticing, like, symmetry is very abstract, very visual. So it's just something that the more times you visualize things, the faster it's going to become. So go ahead and pause the video again and try 15 to 20 on your own. And then check your answers once you're done. Alright, so 15 has all 3. 16 just has point and rotational. The reason line doesn't work is because of where the heart and the face is going to be on the playing card. 17 has none. 18 has just line. 19 has just rotational because of those arrows. That's really effective for having lines. And a snowflake, number 20, has all 3. Alright, go ahead and turn to page 9 for your dilations notes. Alright, so a dilation is the enlargement or reduction of a figure, so making it bigger or smaller. The scale factor indicates how much the figure will enlarge or reduce by. We use the letter K to represent scale factor. When K is greater than 1, the dilation is an enlargement, so it's getting bigger. When K is less than 1, the dilation is a reduction, so it's getting smaller. Don't just assume that every fraction you see is a reduction, because 5 over 2 is actually 2.5, so that would be an enlargement. So don't just assume, oh, it's a fraction, it's getting smaller. Make sure you know what that fraction is. The first one we're going to look at is number 1. We need to multiply all of our stuff. This is the scale factor, so we're getting bigger and smaller, so we multiply everything by the number 2. So since 2 is greater than 1, it's going to be an enlargement. I'm just going to take all my coordinates and multiply by 2. Negative 5 times 2, 1 times 2, negative 3 times 2, 4 times 2, 2 times 2, and negative 1 times 2. And then we're going to plot our new points and make sure we label with times. This is a 10 by 10 grid that I'm doing. And then we're going to connect them. So now we're going to look at number 4. This is a scale factor of 1/4, so less than 1. So this is a reduction, so I should be getting smaller. Since it's 1/4, we could just divide by 4, but sometimes it might be different, so I would practice also multiplying by 1/4 using that fraction key. But if I divide everything by 4 here, it's going to be 1 and 2. And divided by 4 is 2.5 and 0. And then negative 0.5 and negative 2. So let's go ahead and plot our new points, labeling with symbols. Do that 2.5 as fast as possible, and do that negative 1/2 as fast as possible too. And then connect them accordingly. You guys go ahead and turn to page 10 and do number 6 on your own and answer the video when it prompts you to. Alright, still on page 10, just looking at our last two. In this case, we have our figures both plotted. We just want to figure out the scale factor. Alright, and on these ones, we want to identify the scale factor. So we're given our image and our pre-image. So what we want to make sure that we do is actually start at the correct point. So remember, you want to go from your original to your new. Your new is your prime. So you always want to be transforming from original to new, never the other way around. So find the coordinates of one of the points. I like to stay in a straight line, so like I'm going to pick either points E or G, because what I mean by that is notice how only one value is changing. Only one value is changing. So if I find the coordinates of point E, E is located starting at the origin, 1, 2, 3, 4, 5, 6, 0, and E prime is located at 1, 2, 0. Now, some of you might be able to tell what you're doing to one value to the other. But just remember, throughout this whole process, we've been taking our original point, multiplying it by a scale factor to get our new point. So we've taken our original, multiplied by k, and we've gotten our new. So if I take our original, 6, multiplied by k, that's going to get me my new value. Divided by 6, I'm going to get 2 over 6, or better known as 1/3. And as you can tell, that original is getting smaller as you look at your image, so there should be a reduction, so it should be smaller than 1. Go ahead and attempt number 12 on your own, and enter in your answer who you're asked to. Alright, there are a lot of questions we skipped over, so if you'd like any more practice, go ahead and do them, and then you can compare answers tomorrow in class, or ask any questions.